Okay, welcome everyone to today's webinar. This is Stacy Elliott at RheoSense. Thanks for joining us. And today what I wanted to talk about is estimating your shear rate for your application, and then also how to select the shear rate for your measurements specific to our product, our VROC technology. So when I came up with the idea of doing this webinar, I feel that I kind of made the topic so extremely broad, and I also fear that people will be expecting that I can tell them, exactly what rate or rates they should measure at, and that this will work for everyone. But the topic is, as stated, very, very broad, and it really depends highly on, what your goals are, what your samples are, and what your application is, if that's relevant. So the main objective for today is to kind of keep it more introductory and get everyone to start thinking about how to, question what you're doing, let that lead you and guide you to some extent, and then start analyzing your applications in terms of some basic flow configurations. And then in the future, what we're going to do is pick very specific topics and then go into a more detailed analysis. We've kind of done this in the past with injectability or flow through a syringe, a needle in a syringe, but there's countless applications that we could really dig in, and some of them, we've been in contact with some of our customers who have, shared information with us on things that they're working on, and some of the applications are extremely complicated, and you really need to get in there and start breaking it down, because the whole idea of, what I want to emphasize is that even if it's something complicated, you can usually break it down into parts that you can handle with information that's already out there. So let's get started. So first, I always like to recommend that before you start testing, you should really ask yourself some questions, sort of question what you're doing here. Why are you even measuring viscosity, and what is it that you plan to use the data for? So I've kind of thrown out three main reasons why you would measure viscosity. One of these, of course, is, generally you're formulating a product and you want it to perform in a specific application. So if it's a fluid, flow is likely involved, and viscosity will be highly relevant to performance in the application. And then also, ultimately, you have to manufacture these products on a larger scale. So you're going to have to prepare for pumping, mixing, all the processing steps of the fluid. So fluid motion, again, is very important, meaning viscosity is important. And then there are other times when you're just really looking to differentiate samples, and viscosity is a good technique for this. So for example, we know some people who, organic chemists who actually do synthesis, and rather than use some of the other techniques, they like to use viscosity to monitor for changes in molecular weight or polydispersity index. So in this case, you're not necessarily going to link your measurement conditions to a specific application or process, but you're going to choose them to maximize the differentiation you get between samples. So those are some of the things you need to consider. And I also wanted to point out that even if you're just looking at Newtonian fluids, you still need to be careful about what shear rate you're testing at, because the quality of your data is going to be important here. The viscosity isn't going to change because it's Newtonian, but the quality of the data will. So it's very important that you're maximizing signal to noise. So for our systems, for example, and we'll go over, if you're not familiar with our technology, we'll talk a little bit more about that later. So ours is controlled flow and pressure measurement. So if you're operating at the very lowest end of the pressure range, then you're going to have more noise, more error in your data, as opposed to if you're operating mid to high. So, and then likewise on rotational instruments, you don't want to operate outside the torque range. So shear rate is even important for the Newtonian data. Also, there are certain artifacts that you can get in instruments. So one of these is if you go too high for low viscosity Newtonian fluid, you can start seeing what looks like shear thickening but is really turbulence. And then you can have sample loss in certain types of instruments. So rotational instruments, you can have sample flying out of the cone and plate or parallel plates. So I just wanted to point out, I'm not going to say much more about it, but even though the viscosity isn't really dependent on shear rate, to get the best data, you want to pick the right range for your sample. And that's going to depend on your instrument and your sample. So otherwise, if you either don't know what type of sample you have or you know that it's not Newtonian, then you really need to consider, looking at a range of shear rates. And this is especially true when you're dealing with what we refer to as complex fluids. So these would be polymer solutions, polymer melts, protein antibody solutions, colloidal dispersions, microemulsions, things like this. And I've put here that viscosity is dependent on shear rate, temperature, and time. We're not going to focus on the temperature and time or the transient behavior in this case. We're going to really focus on shear rate as we go throughout. But in general, you really need to consider, if its sample is unknown or if you expect that it would be non-Newtonian because it is a complex fluid, you really need to think about, how you're going to measure your sample. So just as an overview for today's talk, we're just going to review what shear rate is, define this. So if you joined us for the last webinar where we were distinguishing between steady shear measurements and extensional measurements, we talked about this, but we'll bring it up again, just so everyone's on the same page and know what we're going to be calculating throughout the talk. And then, as I stated before, some applications are very simple, but other applications are quite complex, and they involve either multiple flow configurations at once or in a series. So you really need to, break it down. So what I wanted to do was, just so that you can start getting the idea of the types of flow configurations that exist and how to handle them and the information that's out there, I picked some common ones. And then I'm going to show you how it is that you calculate shear rate from the velocity profile, because that's how it's done. And then I wanted to emphasize with some experimental data that we have the importance of shear rate when you're looking at sample differentiation or distinction. So this is just some examples of where, if you're not measuring in the proper range, you could mislead yourself or make some improper decisions. And then for everyone who's either interested in using our technology or currently uses our technology, once you've looked at your samples and decided that you do want to measure a variety of shear rates for a variety of samples, I wanted to talk a little bit about selecting our flow channels for testing. So VROC is our technology, viscometer, rheometer on a chip, and I'll talk about that towards the end, and then talk about our options that are available and how you would go about selecting the right flow channel or chip for you. Okay, so starting with what is shear rate. So every time we give a webinar, we always review for everyone, just in case they're not familiar with, what is viscosity. So viscosity, it's a defined property, and it's going to characterize the resistance to a deformation. And it's defined as the shear stress, so it's the stress response to a continuous deformation, which is referred to as the shear rate. That's viscosity, it's a defined property. So when you're doing this measurement, you're going to control one of these and measure the other. In our instance, what we control is the shear rate and measure the stress, which we'll go into a little bit more later. But shear rate is the property we're talking about now, because if you rearrange this expression, it is in the more common form as it's viewed, you can have the situation where viscosity will change with shear rate. So this resistance to flow can be dependent on the deformation. And this deformation, so just then to review again here, the shear rate is going to characterize this continuous deformation or the flow field that we're applying. And it's true that when you have a viscometer or rheometer, this flow field is very well defined because you are having to do a calculation and it needs to be defined. But when you're looking to correlate, what you're measuring to something that's out there in reality, things aren't really well defined out there. But if you want an estimate, you're going to have to go in and simplify, and that's really what we're going to start to go through over the next few slides. So the velocity gradient perpendicular to the flow direction, that's what shear rate is, and we'll see examples of this as we move along. So a shear flow, as stated here, has this velocity gradient that's perpendicular to the direction of flow. And it's referred to as a shear flow because when this is set up, the neighboring fluid elements are sliding past each other, and then this is measuring the resistance. So some examples here are the derivative. So if we have flow in the x direction and the derivative is perpendicular in the y, or flow in the z direction in cylindrical coordinates and the derivative or the gradient is perpendicular in the radial position. So this is just what it's defined as. And when we're going to look through the different flow configurations, what's really going to be important here is the boundary conditions and the driving force for the flow. So the driving force is going to give you, in a sense, a magnitude of what this gradient will be, and the boundary conditions will also define whether it's, for example, a constant gradient across the cross-section, or if it varies in some other way. So so that's the basis of shear rate. It's just to summarize quickly here. It's characterizing the continuous deformation, because steady shear is basically setting up a gradient in the velocity perpendicular to direction flow. That's what shear rate is defined as. And as we move through some of the examples, what we're going to look at, so because it's defined as a gradient in velocity, we need to look at the velocity profile. And so we're going to look at different flow configurations that have different boundary conditions and driving forces that are common, and the fluid mechanics has been worked out. Okay, so starting with the simplest case, and this case is actually what certain rheometers established during their flow process. So this is just relative motion between two surfaces. And if you can relate your process or application to this example, then this is probably the easiest by far to try to handle. So what we're looking at here is two surfaces with a fluid in between with some particular height, h. And one of the plates, although you could have both plates moving as well at different speeds or in opposite directions if that's relevant to you, but this is the simplest case. So for example, we have a stationary base plate and the top plate moving along at some velocity, d sub s. So the sample is fully enclosed. What we're introducing is relative motion between the surfaces, and we're controlling the velocity of the surface, and we're going to employ the no-slip boundary conditions. So what I've drawn in place here is the velocity profile that exists for a Newtonian fluid. And it's just linear across the gap. So zero velocity at the stationary plate, and the top part of the fluid is moving along with the plate at that velocity. So it's a linear velocity profile. And I'm not sure if I mentioned it yet, so sorry if I'm being repetitive, but in case I did not, I wanted to point it out. So as I go through the examples on the different flow configurations, what I'm using is the fluid mechanics that's been worked out for Newtonian situations. And the reason is if you have some sample that you don't know how it's going to behave, and you don't know anything about the rheological properties, then you need to start somewhere in terms of estimating what range is important for your application. So start with the Newtonian case, and that's going to guide you and give you a good estimate of what's appropriate for you. So in case I didn't mention that, everything we're talking about initially here, it seems somewhat contradictory. I'm telling you that your sample is probably Newtonian and you need to measure viscosity as a function of shear rate. But the fact is, unless you're able to do computational fluid dynamics, a lot of the more complex rheologies, the fluid mechanics is not worked out, and it's not something that you can do analytically. So in terms of setting up your experiments and getting some guidelines, it's perfectly acceptable and standard to look at the Newtonian case. Okay, so this so we've established then that the velocity profile is linear across the gap, and this means that so here's a good view of when I was kind of awkward on the last slide when I was trying to discuss the shearing motion and the relevance of the velocity gradient perpendicular to flow. But here it's very clear that you have, I'm using the general convention here. I'm not sure if you're not, if you haven't taken fluid mechanics or dealt with engineering, I'll just point out that what this plot is intended to display is the arrows, the length of the arrows represent the magnitude of the velocity in this case. So we go from the max velocity down to the zero velocity. And so you can see this visual gradient perpendicular to the direction of flow. This is the definition. So shear rate then in this particular case is a constant value, and it's just related to the velocity of the surface divided by the gap height. And as I stated, this is like, if this is your application, then this is by far the easiest one to approximate. So this is very common if you're doing any type of spreading process. So this would be paints, coatings, spreading food products, spreading topical personal care products onto the skin. And then also it's, analogous to what's happening, when you put eye drops into the eye and your eyelids are blinking, going through the blinking cycle. So, and I just wanted to point out that, we've worked with certain customers, although we're not going to elaborate on, all the possible things that could happen with this type of flow. I just wanted to point out that we've worked with different customers who have, for example, rather than using a uniform top surface where they were spreading a product topically onto the skin, they had a paddle that had a texture to it. And so basically in that situation, you had different fluid gaps across the plane of the paddle. So what you could do is you could go in and say, knowing the texture of your paddle, for example, you could go in and calculate a range of shear rates that would exist within the system, from the narrowest gap to the thickest gap on the surface. So you can take this and then you can, keep it simple, but add in some more additional information. Okay. So another one of the common flow configurations is a pressure-driven flow. So in this case, we're looking at something that's fully enclosed. Again, now, however, the boundaries are stationary, but we're still keeping the no-slip boundary conditions employed. And we're going to control flow rate or pressure drop. And so now what you can see is we have a very different velocity profile that exists. So here we're looking at cylindrical geometry, and we're defining Q as the volumetric flow rate, R as the radius of our cylinder. So now for Newtonian fluid, it's worked out how the velocity profile changes across the cross-section of the tube, and it's just a function of the volumetric flow rate and the radius and the position along the cross-section. So now in this particular case, what you see is we have a parabolic profile. And knowing that shear rate is the derivative of the velocity profile at any given position, now we have a shear rate that varies across the cross-section. So its maximum at the wall goes to 0 at the center. So now, a fluid that is being pumped through this system, if it's non-Newtonian, it would essentially behave differently at each point across the radius. Now, when you're starting to look at, as I stated, what range of shear rates is appropriate for your sample, starting with Newtonian is fine. However, I drew this, I added in the basically compressed velocity profile here in red, just because I wanted to mention that there are certain specific cases for the different geometries that are worked out for very simple non-Newtonian behavior. So this red curve is something that you would have if you have a power law fluid. So if you first start off by, the Newtonian case, you go and measure some data and you realize that your fluid is power law dependent with shear rate, then you could go back and refine the process using that solution. Although I wanted to keep, there's already enough equations, so I wanted to keep those down. An example of where this is relevant, or any time you're pumping fluid through some circular or cylindrical conduit. So this would be, and we've talked about specifically in detail about flow through a syringe or a needle and what that means to injectability. Anytime you're dealing with flow through a pipe or tubing, so in processing, variety of processing techniques. And also you could even go down to, say, if you had cylindrical pores in a filter, it's going to apply to that as well. And I just wanted to point out, and let me just step back to the previous page just to get a feel for, what kind of a process would be high shear rate and what kind of a process would be low shear rate. Some of the key factors are obviously, so let's look, I jumped back to the relative motion slide so that I could, because this is the easiest to view. So if you think of something that's in a very thin film where the H value is very small, so the smaller the film gets, the higher the shear rate is going to be. So anytime you're dealing with very thin gaps or films of material that have a reasonable driving force, then you're starting to move towards high shear rates. Likewise, when we're looking at the pressure-driven flow, when you're looking at flow through a needle where the inner diameter is, sub-millimeter, again, because the max flow rate, or rather shear rate, is inversely proportional to this inner diameter or inner radius, then the rate is going to go up. So smaller dimensions are always going to increase the shear rate. Okay, so another flow type configuration, just to start showing some different things that are out there. So the other the flow configurations were confined. The fluid was confined between two surfaces. But there's also the possibility that you have something that has a free surface. So the fluid is bounded by one solid surface and open to the atmosphere on the other side. So this particular free surface flow is a gravity-driven flow. So basically, although it could be an incline, I took the simple case of the vertical wall and this thin film of thickness h on the wall. So now the driving force of flow is going to be gravity alone. And so now we were able to work out the velocity profile, which again is sort of a half parabola here, because unlike the boundary conditions that exist in the confined geometries, the boundary condition that you have to apply at a free surface is actually a zero stress condition, as opposed to the non-slip, because ahead of time you don't really know what the velocity is going to be out at this point. So we've applied the no stress condition, no slip at the wall though, so it's stationary at the wall, and we were able to determine this sort of half parabola as a function of film thickness. So again, just taking the derivative of this velocity profile to get the shear rate, we see that it's linear, and it's maximum at the wall, and the shear rate goes to zero at the interface, which it would have to do to satisfy the no stress condition. So in this case, so examples of application here would be any sort of vertical film that you would apply. So this would be paints or coatings. So you could think of paint on a wall, something of this sort. In this case, even though the film would probably likely be very small, because the driving force is only gravity, in this case the shear rate is going to be much, much smaller than you might expect for another thin film that actually has some pressure-driven or relative motion flow. So this is another example now we had with the free surface. So I wanted to include then something that would be a little more complicated to show that you can start mixing driving forces essentially. And although you could mix pressure-driven flow with a moving surface, but in this case I mixed the gravity-driven flow with a moving boundary. So now what we have multiple driving forces here. So we have again a thin film. Now we've put it on an incline, and we still have gravity acting on this free surface, but now we have the base plate moving at some velocity v sub s, moving up. So you can imagine if you're coating a substrate and the base of the substrate is moving through the atmosphere or your environment. So in this case, we again have the free surface where we have the zero stress boundary condition, no slip at the moving base, so the velocity of the fluid has to move with the base, and we kept this gravity contribution here in place. So again, our film thickness is h, we're at some incline theta, and in this case now what you see is, and this is a sample parabolic profile. The exact form of this would be highly dependent on the film thickness, the viscosity, and the speed of the base. But this is an example of what you could see, where you have motion towards the plate moving in the positive direction, but because gravity is present, it can be moving in the opposite direction towards the interface. And again, I wanted to emphasize that the exact shape of this profile. It could, if you're moving at a very fast speed, the base plate, it could be entirely positive. But if you're not moving so fast, depending on the application, then you should be aware that you could have flow in multiple directions within the thin film. So again, if you want to look at shear rates that exist in this type of flow configuration, you would want to take the derivative of the velocity profile perpendicular to the direction of flow, and in this case, it's going to be a linear change of shear rates across the gap. Again, the max shear rate is going to be at the moving plate and zero shear rate at the interface where you have the no stress condition. So, and as I mentioned, this is just one type of mixed flow. You can have the case where you're mixing pressure driven plus motion of a boundary, and then you can see a variety of distorted shapes and the possibility of flow in the opposite direction. So one other thing I wanted to point out as we're sort of gone through these examples, and we've emphasized that when you're getting started and you're trying to break down what your application is, what type of flow configuration you have, it's okay to assume initially that things are Newtonian just to get the numbers to get started. And sometimes in certain flow configurations, due to the nature of the driving force, you're going to have to estimate a viscosity. So when you're trying to get your range of shear rates, sometimes you're going to have to also come in with what you think the viscosity of the samples might be to sort of narrow it down. So I just wanted to point it out that this is by no means, you can't perfectly pick things, but you can certainly use this to get started and guide yourself. So that's sort of just to get you started thinking about what type of flow configuration you might have and how you might go in and extract the parameters to start estimating shear rates. So, fluid thicknesses, relative motion of the surfaces, flow rates or pressure drops, things of that nature. So now I want to move on to actually what's kind of more of a simple topic. And that's, so if you remember when we started, we were asking, why are you measuring viscosity? Is it for a specific application? If that's the case, then you want to start analyzing your application using some of the ideas that we just presented, trying to break down the look for simple flow configurations and then try to work from there. But if you're just looking for sample differentiation, then you don't necessarily have to calculate anything ahead of time. But you really want to think about what you're trying to differentiate and what type of samples you're looking at. So I have some examples of data where we're looking at viscosity as a function of shear rate, and just sort of emphasizing that, if you're trying to use just a single point viscosity measurement, which is quite common with people, they think of viscosity as just one number, and you can get one number and it will tell you everything you need to know, then you can run into some difficulties. So here are some examples where, so on the left we have viscosity as a function of shear rate, and this was some testing that we had done where we were looking at real maple syrup versus fake syrup or pancake syrup, and then mixing the two together at 80-20%, 80 real to 20% fake. So the reason we were looking at this, just a quick backstory, was that apparently there's counterfeit product out there where it's predominantly where they cut the real product with a cheaper ingredient to cut on cost. So it's not really pure, but cut with something artificial that's less expensive. So one of our customers was questioning, can you distinguish the real stuff versus the fake stuff and something that's mixed in between? So that's the nature of this test. So if that was your goal, was to analyze these samples and distinguish, whether it's real, whether it's fake, or whether it's a mixture, and to what extent have you cut the sample with the fake product. So I sort of highlighted a couple of regions here. So when we did the experiment, we did a range of shear rates, and we got quite a bit of information. So on the whole, what we're seeing is that when you look at the viscosity of the real maple syrup, there's minimal change in viscosity with shear rate. Whereas when you look at the fake syrup, there's quite a bit of shear thinning that occurs over this rate range. And there's a couple points I want to make here. In addition to just doing the experiment where you're scoping things out, because one thing that you could do, you don't even necessarily have to think about the samples that you have, and you could just say, okay, I'm going to do a broad range of shear rates. I'm going to see where I can maximally differentiate the samples, and then I'm going to focus there. And that's sort of what I've highlighted with the circles and the sort of elongated shape here. If you thought you could just pick one rate and you made the mistake of picking a rate down here around 50 inverse seconds, you would say all of these samples are exactly the same and there's no difference, and you can't use rheology to distinguish them. However, if you did the full experiment and then realized that, if for QC purposes you didn't always want to do a full shear rate analysis, then you could focus in on some higher rate, somewhere around 2,000 plus inverse seconds. And you could also, that's just looking at the data after you sort of do a brute force scoping it out. But you can also think about, the samples that you're looking at. So for example, the real maple syrup is predominantly just sugars, and then you have some minerals and maybe some amino acids and tiny amount of proteins. The pancake syrup, however, even though it's the absolute last ingredient on the list, it does have xanthan gum. So xanthan gum is a very high molecular weight polysaccharide. It's added intentionally to achieve high significant shear thinning. So, knowing that what is in your samples, knowing that the faked product has this common rheology modifier that's added to introduce shear thinning, knowing that the real maple syrup shouldn't likely, given its formulation, change too much, ahead of time you could probably make an educated guess and say that shear rate dependence would be important here because of these two factors. The real maple syrup being more of a simple sugar solution, this pancake syrup being more of a intentionally modified product with a high molecular weight polymer in it. So it's kind of a lot there for me to say about this one plot, but you can think about it in terms of make educated guesses, or just do a brute force approach and then sort of narrow it down for your QC analysis. So as another example, again, viscosity is shear rate on the right-hand side. These are actually two eye-dropped product formulations, commercial drops that we've purchased over the counter. So the red curve, the main ingredient is hydroxypropyl guar, and you're not going to be able to differentiate your samples. So, I've highlighted the region out here. If you chose to measure at a higher rate, in this case, they would look identical. But if you were measuring at a lower shear rate, you would clearly be able to distinguish these two products from each other. So this is just, the main point there. Okay. So another comment I wanted to make about, when you're measuring, trying to select shear rates that you want to measure. We've had comments in the past about, can you measure zero shear plateau with your system? And I think there's a little bit of a confusion about that this zero shear plateau means that you have to go to an actual approach a zero shear rate. So I wanted to point out that this is not true, and just again emphasize how different samples, the rheological behavior can vary so dramatically. So these limiting plateaus, so I mentioned the zero shear plateau, but there's also what's referred to as an infinite shear plateau. And these are not universal, but they're highly sample dependent. And so you're really going to have to think about what sample you're measuring and where can you access this, if you can access it at all. So we have two different sets of data here. On the left, this is actually some more xanthan gum at various concentrations over a range of shear rates. And on the right-hand side is viscosity as a function of shear rate for some concentrated protein solutions. And so what we can see is, so we've plotted them on the same scale from 10 to about 200,000 inverse seconds. And we see on the left-hand side, we're even at about 50 or so inverse seconds, we're well into the shear thinning regime and not even close to any sort of plateau. Whereas with the concentrated protein solution, even up to, for one of the samples, towards 5,000 inverse seconds, we're still in the plateau range, in this Newtonian plateau. So just to, again, redefine what these plateaus are, they're, even if you have non-Newtonian behavior, in theory it's possible that if you go to the extreme conditions, either low shear or high shear, you can reach this Newtonian plateau. So that's what we're referring to here. So it's important to realize what type of sample you're looking at. So with the xanthan gum, as we had mentioned before, this is a very high molecular weight polymer, in excess of 1 million. It's polysaccharide, so it has a cyclical structure there. It's quite possibly, even at low concentrations, in some sort of entangled state in a polymer network. And so it's going to behave very differently than these much lower molecular weight, smaller gamma globulin molecules, which are going to be more similar to a colloidal system, a small colloidal particle. So, it's just emphasizing that this sort of behavior of systems is not universal. You have to really consider what system you're looking at and what's the proper range to access something like a plateau value. Okay, so with that in mind, I wanted to skip into some comments on, if you use our technology or are interested in our technology, what options are available, since we've sort of emphasized that, you don't want to use a single shear rate to differentiate samples for most cases. And if you want to actually test to predict for your application, it's quite possible you're going to want to test over a broad range of rates. So I wanted to talk about, because I think there's also been some confusion with some people interested in our products, that if you buy one particular flow channel, then this might work for all of your testing. So that's why I wanted to elaborate here a little bit on our technology and how, if you really want to do a broad range, you're going to need to access a number of flow channels, perhaps. So just in case someone's not familiar with our technology is what we've referred to as VROC, which is viscometer rheometer on a chip. And so here's a schematic of what the flow channel would look like. So this is a combination of a microfluidic flow channel with MEMS microelectromechanical systems sensors below. So these are silicone pressure sensors that are distributed across the flow channel. So what we're doing is we're controlling the flow rate into the channel, and we're measuring the pressure drop across the flow channel. So this is just an example of pressure as it drops. Pressure is a function of position as you move through the flow channel. So the pressure drops as you move from the inlet to the outlet. And as I mentioned, this is a controlled rate experiment. So we're controlling the flow rate, which means we're controlling the shear rate. And we just calculate the shear rate dependent on this rate, the flow rate that we're applying, and then also the flow channel dimensions, the width and the depth of the flow channel. What we're measuring from the pressure sensors is this pressure drop across the flow channel, and that allows us to calculate the stress, again, including the dimensions of the flow channel. And this is how we calculate the dynamic viscosity. So what we offer up are a variety of flow channels and flow testing configurations. And by testing configurations, one of the main factors is the sample that you are able to pump through the flow channel, either because of what you've loaded into our automated system or because of the test syringe the volume of the test syringe that you're using. So the next thing I wanted to go over are some options that we offer, and sort of, it is quite a lot of information to dump on one slide, but I wanted to put it out there that we offer a lot of options. And if you want to measure a broad range of shear rates for a broad range of materials with different viscosities, you're going to want to explore these different products that we have. So I just described the flow channel, which has fixed dimensions and a fixed pressure sensor range. So what we offer then are variations in the sensitivities of the pressures. So we generally categorize these with the letter category. And it ranges from a max pressure of 10 kilopascals to 1800 kilopascals. So one thing that you want to consider when you want to measure a variety of samples at a variety of shear rates is what is the max pressure of the flow channel that you've selected. So I've thrown out here just basically a simplified relationship where, so the max pressure that you'll have is at the leading pressure sensor near the entrance. And this is sort of what you're going to be limited by. So you don't want to go above 100% of the max pressure scale. And this pressure that you're going to experience is going to be proportional to the viscosity of your sample times the shear rate, or also the flow rate. So I put this here just to point out that the higher the viscosity your sample is, you're going to be more limited on the max rate that you can achieve, because it's the product that really defines the max pressure that the channel is going to experience. So higher the viscosity, you're going to be more limited on the flow rate or shear rate that you can obtain. Likewise, if you really need to get to a high shear rate, you're going to be more limited to looking at that flow channel with lower viscosity samples. So that's something to consider when you're deciding on, your testing is, what is the product of the, approximate viscosity times the shear rate that you're looking to test at. And then how does that compare to the maximum pressure of the flow channel that you have or want to have. The other factor is, so that we're going to look at this sort of top table now, is how much sample volume is available for your testing. So if you're familiar with our technology, we have multiple instruments. So that core technology that I mentioned is available in a variety of instruments. And the exact configurations vary. But the main point I wanted to make by including this is that the other factor when you want to go to very high rates is that just conservation of mass. You're going to need to pump more fluid through the flow channel at the maximum shear rates that can be obtained. So if you're trying to work with either in the case of our automated system, a very low loaded volume into the test syringe, then you're not necessarily going to get to the max shear rate available. Likewise, if you're using a small syringe for one of our manual systems, you're going to have to factor that in too. So it's not just the pressure sensors that are important when you're trying to select the range that's going to work for you. It's also the sample volume that you have available for that particular test, either in the form of loaded in our automated system or with the particular volume of the syringe that you're using for the manual systems. So those are just the key points when you're selecting the products for your use. So I wanted to I like to view this graphically, and the instrument I probably use the most is our automated system, which is what we refer to as the initium. And so this is a specific flow channel that is available for our automated system. So it's the B, so that's, let me jump back here one second. So the B flow channel has a maximum pressure of 40 kilopascals, and this is a B05, so it has a channel depth of 50 microns. Now the initium instrument really at this time only comes with a 100 microliter syringe, testing syringe. So, however, what can vary is the sample that you actually load into this. So let me try to make this clear. So I like to look at this graphically. So that's the system that we have. It's our automated system with that particular flow channel. And what we have plotted on the left vertical axis is flow rate, if that's what you'd like to think of, and on the right vertical axis is shear rate, if that's how you want to think of the deformation process. And then on the x-axis is viscosity. And so as I mentioned, the exact testing limits are going to be bounded by both the pressure sensors and then the fluid volume that's available for the testing. So in this diagram, the pink dashed lines correspond to the range of the pressure sensors. So below this line here, you're below the range of the pressure sensors, so you would just have too much noise in the data and it's not appropriate to test. If you go above this pink line, now you've exceeded the max pressure and then you're potentially damaging the product. So just to be a little more clear, if we have a 100 centipoise viscosity sample, we can start testing somewhere around either 2 microliters per minute or 40 inverse seconds, and we can go up to this point about 600 or 800 inverse seconds. So this moving, vertically between the two pink lines is basically looking at what is our pressure range. But then, as I mentioned, the sample volume is also relevant, because you higher rates, you're going to just have to pump more fluid through the channel, just the conservation of mass. So what we've also added here are, that with our automated system, I'll just point out that one of the big factors people are interested in is using minimal volume. Customers for this like to use as little volume as possible. So sometimes they try to get away with as little as 26 microliters. So our top line here, this dark line, indicates if you've only have 26 microliters in the syringe. And then if you're able to work with, say, 34 microliters and then up to 50 microliters. So what you can see is if, in certain shear rate ranges, or rather viscosity, for certain viscosity samples, you're going to be further limited, and in this case, not by the pressure sensors, but by the volume that you actually have there. So if you're working with something at, say, 10 centipoise, and you only have 26 microliters to work with, you're not going to be able to reach the full pressure scale. You're going to be limited to a lower shear rate because of the limitations in the volume. So that's just sort of, and you could basically plot something out like this for all of the flow channels, considering, the pressure range, channel depth, and then the volume available, either with whether it's loaded volume with the initium or test syringe with one of our automated systems. So that's just sort of a guide on, what you can test with your flow channel if you have our instrumentation, and then how you might select the product if you're interested in moving towards it. So let me just summarize that, shear rate and what rates you're going to look at are very important. It's even important, I would say, for Newtonian fluids, not necessarily because your viscosity changes with shear rate, but because you want the best data quality possible, and you want to avoid artifacts and noise and such. For specific applications, we sort of started looking at, the idea was to get you thinking about, you may have a very complex application with very complicated flow patterns, but generally you could break it down and start, breaking it down into sort of well-known simplified flow configurations, either one or many, depending on what you're dealing with. And it's fine to start with the fluid mechanics that have been worked out for the Newtonian case, because you don't really know, the rheology may be so complex that there is really no analytical solution for your sample, or you just may not know ahead of time. And this is really, you're looking for something to ballpark and get a reasonable best guess for. And then use this to determine a range of applicable shear rates to get you started on your measurements. And then also just to reemphasize that, even if you're not dealing with a very specific application that you want to predict performance for, it's always better to consider doing many rates when you're dealing with, just sample differentiation. And you can either just do a brute force approach and try to, ahead of time scope it out and then scale back if you want to do some sort of quality control type analysis. Or you can start thinking about, what is in your samples. Do you expect them to shear thin because they're polymers, high molecular weight polymers, or strongly interacting colloidal dispersions, and sort of go from there. So thank you for your time. Again, I'm so sorry for the situation with the audio. So I think most of our questions, initially anyway, were related to lack of audio, but let's take a look and see if there's anything else we can address. Okay, yeah, I understand that because of the, we had no audio, it's going to be tough to inquire. But yeah, again, we apologize for that, and but we'll send everything out, and then so I think what you would have missed at the beginning is that this is a general overview. I wanted to get everyone to start thinking about shear rate, why it's important, how you can start in a very simplified way analyzing your applications. And in the future, what we're going to do is follow up with very specific cases. So because it was hard to, there's infinite applications that exist out there, from injectability to countless coating processes. It was hard to try to incorporate everything. It would just have gotten, too much. So, moving forward, I think that's what we'll do is we'll, sort of build upon what we've laid out here as kind of a foundation, and then come back and say, okay, here's the specific application. Now I'm going to apply the tools that we talked about before. So I think we'll end it there. Thank you so much for attending. And again, thanks for your patience with us, and have a good day.